Yeah, I can see a screen.
So NumPy, I didn't prepare a presentation as such for this thing, but um, this is some code that I have written to take you through, and we have some uh, what do we call web pages also that I have with me. Now the the basic thing about NumPy is that it's a package for doing numerical uh, array operations, for managing numerical arrays. So NumPy stands for numerical Python, and the beginning, you are familiar with indexing, right? You were saying that
Yes,
um,
yes. Yeah.
so indexing is one of the ways that these NumPy arrays can be accessed. But over here, we start with that. Basically, first thing is that you have a Python int list, as you can see over here, 1, 2, and 3. Now, the difference between a Python int list and a NumPy int list is that the first thing is of initiation, and if we can initiate, how do we initialize and create, how do we call the constructor of NumPy array class, nd array class, to create a NumPy array. And if we call the type function on it, it would return a Python int list would return you list, this kind of expression that it is of class list, while a NumPy nd array would say it is of this is the output if we call the type function on a variable for which the NumPy array. Now broadcasting is are you familiar with broadcasting? So Python int list is that if these are three numbers, and if we add 5, if we try to add 5 to them, now what would happen is that Python int list would fail. Why? Because when we say +5, basically it tries to think that this is a string, or it is not an int, and concatenation operation is happening. So if we should if so basically this would fail, because we cannot add 5 to a list, because we can either add let's say concatenation can happen, but plus operator would work with numbers or with strings, such as this, or this, let's say hello space world. So these two would work, but this one would fail if we try to add 5. Now NumPy overcame this thing. NumPy, we have a NumPy array with 1, 2, 3. When we add 5 to it, it broadcasts 5 to every element. 1 plus 5 is 6, 2 plus 5 is 7, 3 plus 5 is 8. And this works as well for multiplication. If
Can you
we
scroll up? Okay. So to add a number or do any suppose multiplication or addition, we cannot do it directly on list. We have to convert it to array first.
yes,
Is it?
you must be familiar with that Python acts like a calculator, like we can see over here. If I'd open a Python shell, right? Python shell acts as a calculator. This, and
Hmm.
5 times, okay, 2 times 3, 6. So it acts like a calculator. If we pass it hi and another string, it would concatenate them. Hi, hello, hi, Ram. So hi Ram, it concatenates. Now, if we have a list such as 1, 2, 3. Now with the list, you can list, if you want to add all of the numbers, add 5 to all of the numbers of a list, you would have to do something like this. L list comprehension. It is L I plus 5 for I in L. Now L gives you 6, 7, 8, right? This is the list comprehension expression. And this expression is called list comprehension. I square bracket I plus 5 for I in L. Now, what if we want to make it simple? Now, NumPy is a numerical Python package that makes it simple. It has a class. So because our L does not have any string object, we can create a NumPy array from it. And the way to do it is we would say lijklm equals to np dot array L. Now, if we, what we were doing over here, right? We have modified L basically. And so M, it says, is an array. Now L, we cannot add 5, but we can subtract. Now see this, to subtract all, to get L back, 1, 2, 3, and we cannot do it to L because it's a list, but we can do it with array. So if we want to do, let me see if it works. L 1, 2, 3. Now this operation is called broadcasting. Basically, 5 is being broadcasted with the minus symbol to every element in L. So first we had 1, 2, 3. We added 5 to every element using list comprehension. Then we use NumPy package to get our L back to 1, 2, 3 by the help of broadcasting. M minus 5 is broadcasted to every element of M, and 6 minus 5 is 1, 7 minus 5 is 2, and 8 minus 5 is 3. Broadcasting is clear?
Mm-hmm.
Okay, now
Yeah.
I'll copy it. Okay, broadcasting is clear. So checking the type of variable is basically a normal Python operation. Broadcasting we have covered. Factorial is basically that we have a function. Factorial is you have a number such as 5. Now factorial of 5 is 5 times 4 times 3 times 2 times 1, 120. Factorial of 4 is 4 times 3 times 2 times 1. Now we have to implement this thing using NumPy. How do we do that? Well, NumPy gives us an arange function. Arange function is kind of the range function that you must have seen in range 0 to 10. So it will give you all of the elements from 0 to 9. Otherwise, if you don't want to use that, we can use NumPy arange, and this also gives a similar same thing. If we say 1 and over here we say 10 or 11, it will give us all the elements from 1 to 10. This is exclusive of 11. And 1 second, and exclusive of 10. Okay, now how do we now we were speaking of factorial over here. This is a simple mathematical function that we use that we implement using NumPy. Now cumulative product is, this is not, so NumPy is a numerical package. We at times have to do a lot of numerical computations. We do not need to remember them all. Basic understanding of NumPy would help us get started with using this package, and after that we can refer the documentation. But basic understanding is a must, such that if x is equals to, let's say, a range, it contains elements from 1 to 5, exclusive of 5, 1 to 4. Now, when we do a cumulative product means whenever you say see it cumulative, right? That means you are not ignoring the previous thing, such as if I'd explain in machine learning and num in this mm, statistics, we have this thing. Let's say this thing is 1 and 1. Okay, now we have one element over here, and I this 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 this. Now if let's say we want cumulative frequency, if we want to simply get the frequency of a, let's say, frequency of doorbell, and these are the timestamps. Let's say this is timestamp 1, timestamp 2, timestamp 3, timestamp 4, timestamp 5. Now, frequency meaning whether we had a doorbell or not. Now, if we have a doorbell, we would have something like this and like this and 1 and otherwise 0, right? So I'm explaining cumulative frequency to you, cumulative frequency over here. And if we have, this is a helpful operation in, let's say we have this some kind of, and I just, for the sake of demonstration, I'd add one more over here, and this is 6. Now if we draw a chart over here, this is the plot of number of times and a tabular data. We can have a tabular data of this sort where we have timestamps and frequencies whether or not the doorbell rang. 2, 3, 4, 5, 6. Now 1, 0, 1, 0, 5 is 1, 6 is 1. Now if we talk about, if you hear the word cumulative, that means all of the previous instances will be considered and not ignored. So when we say what is the cumulative frequency of this data, we would say this is the plot, and this is 1, 2, 3, 4, 5, 6. So we have this is 1. Okay, now we would say over here it is 0. So 0 till here, then 1, then it continues to be 1, then we add 1 to it. Let's say this is 2. So this is 2. This is 2. It will go on until here, and here it will increase 3 and 3, and here it will increase to 4, something like this. All of the previous values have been added. Now this is what we are going to use for our factorial function. Now factorial function, cumulative product what happens with cumulative product is we don't miss out anything from this array. If we start from here, 1 times 1 is 1. Product means we are basically do the multiplication. 2 we will get 2 times 2. 3 we will get 3 into 2 into 1. 4 is, let me try to print x dot tab, product is there, 24. So this gives us what is the product of all of these items that are here in this array. Now, if we do the cumulative, it returns iteratively that for every element, return what is the product for previous elements. 3 times 2 times 1 is 6. 4 times 3 is 12. 12 times 2 is 24. Now, this was about the cumulative product, and we can use that in this way. If we want to find out factorial of a number, we would simply initialize a list, such as shown over here. If you want to find out factorial of 5, then we would initialize a list, factorial of 4, then we would initialize a list of n plus 1, because we also want 4 in it. And then once we have the list, we get the cumulative product and we get the last element. And from this way, we have written a factorial function. Well, if we wanted to get the factorial function right, we could have also done the product. That would have also returned instead of this. I got it from the book, but instead of cumulative product, we could also do the prod, and that would also return the factorial as we are seeing over here. 1, 2, 3, 4, and this number and this number is same. So basically product would have also worked. Now, is this, are we clear till here? This is one of the use cases of NumPy, nothing serious in it. Remember what is cumulative, what happens when the term cumulative, when you hear cumulative summation or cumulative product or cumulative frequency, the previous instances are not forgotten, and you don't get something like what we are seeing over here, like individual instances which are like discrete, which are like in independent instances, but instead of like a summation, we are summing over here, we are trying to find out cumulative frequency. This curve can be discrete as well as continuous. Over here in this example, this is of discrete. Discrete means that we have got fixed values 1 0 1 0, and it's not continuous. I'd show one more use case of NumPy, and that is with multiplication. Two types of matrix multiplications. Let's say we have a matrix called such as this A. Now if we have 1 minus 1 1 2, then if we try, and a matrix P, which is again two-dimensional matrix, number of dimensions, number of rows is, so it has got, if we have, we can, hello?
Yeah, I'm saying 2 rows, 1 column.
2 rows, 1 column. Yeah, that is correct. And we can check it also like this. If we want to check it, there's a method called shape that is present in the pandas as well. B dot shape. A list object has no
Square brackets.
NumPy
Oh, sorry. Non-brackets.
shape. 2 rows, 1 column, as you were saying. Now, if we try to do a multiplication like we normally see with lists, this won't happen. It would say we can't okay, basically these are lists, and you can't multiply lists like with a asterisk operator. But if you have a NumPy array, if these arrays are converted into NumPy arrays, like we are doing over here, np dot array, and we print them 1 minus 1, 1, 2, then np dot matrix multiplication is that these two are multiplied with these two. And are you familiar with matrix multiplication, or shall I show it? I'd show it, I think so. You
You
know,
can skip that.
okay, I can skip that. Well, basically, if you want to do the matrix multiplication, you have to call the matmul function, not this not the asterisk one. And if you, there are multiple kinds of operations. If it's a vector operation, if you want to do vector multiplication, then what you can do is matrix multiplication. You would have to call matmul, and for that there is a condition that number of columns.
It should not be vector.
What?
The two numbers should not be vector.
The two numbers which?
Because vector is nothing but single one dimensional, correct?
Yeah, vector can be multi-dimensional as well. Vector, yeah, it's a, well, if it's a point, there will be only one dimensional array. If it's a point, every dimension would have. But if it's a line, then it will be in two-dimensional. If we have, 1 second, if we have,
Sorry, not dimensional. Suppose in matrix we have 2 by 2. So matrix, I'm saying it is always 1 by 1. Vector, sorry, vector is always 1 by 1.
yeah, point vector is always one by one. Okay, so
Sorry, 1 by 1, no number of elements. It's always one column, I'm saying. Is it correct or not? Vector is supposed to be one column with multiple elements.
Vector is not supposed to be one column. You have heard of line, right?
LIME?
Yeah. Okay, so I apologize. 1 second. Let's say, how do we represent this line? Line would have in, so basically point, yeah, vector is always up. Yeah, yes, you are right. So basically, if this is the point and this is x comma y, then it means that this is the vector. And yeah, you are right. So number of rows would always be one, but if it's a matrix, then it would have more rows. But if it's a vector, it would always be like xi, x2, x3, and x4. This is what you are saying, right?
Yes, multiple elements, just y would be 1. Then.
Yes. So over here, if we have matrices and we want to do matrix multiplication, we would call matmul. If we have vector and we want to do a dot product, then we would call np dot dot. So np dot dot is there, and np dot matrix multiplication is there. These are two kind of multiplications that we would have. We would dig a bit deep, and
for vectors we have dot and dot product, and we have for matrix we have matmul.
Matmul, yes, correct. And then there is one more, np dot multiply, which is basically that what is happening if we have a dot b, right?
What's the difference between matmul and multiply?
Matmul is matrix multiplication. Why with your, okay, I just copy it. 1 second. This is matmul. This is matmul. Okay, you are able to see, and this is multiply. A is 1 minus 1, right? And B is 3 4 3 4. So when we do a matrix multiplication, this
Or both A and B are similar, right?
yes, A and B both are same. A and B both are same. We are never changing A and B like shown over here in this post.
Okay, yeah.
So I'd just brief you again. When we are doing matrix multiplication, such as we do A and B, these two elements will be multiplied by these, and we get this. Okay. Shall we check? 1 times 3 plus -1 times 4. So that is minus 4 plus 3 minus 1, right? This is -1. And if we want to do the second element, so I'd say 1 times
3 plus 8.
yeah, you got it right. 4 times 2. You got it right. 11.
Yeah. It is
So
simple matrix multiplication we generally do.
yes,
And what is
yes.
NP dot multiply?
What NP dot multiply is basically doing that. I
Simple multiplication.
Yeah, simple.
Yeah, simple multiplication it is.
So element wise multiplication. 1 dot minus 1. So this is multiplied by this, and these two are multiplied by this.
So NP dot multiply and I think dot are same.
No. Dot is
Just
also different. So dot I'll
bring
explain.
three
So
dot also.
so matrix multiplication is clear, and dot I'll explain. 1 second. This is dot product has a bit of two definitions. Two definitions in the sense they will both result in the same answer, but the way we arrive at them is you were seeing two vectors over here, right?
Can you go back to that previous example?
Previous over here.
Yeah, in this we had three, like matmer, then dot, and then NP dot multiply.
Yes.
But there were three in one example, right? There was one block.
Yeah.
So go to
1
the block.
second. This is here. So this is there. This.
Yes, this one. This one. In
So
this we have dot A. Yeah, 1 second. A dot B. Yeah, just take this A dot B also, no?
okay. A dot B also. Okay.
This with this error.
With this error. Okay. NP.
Yeah, that's it. Hmm.
11. So A dot B also is giving us something like why is this happening? Now A dot B, if we do object has no attribute, dot won't work. NP dot. So
No, at this time A is changed. The A is different for dot. You said it is always vector with dot.
it is
Can you
not
check?
no, it is not like it is a vector. Basically when dot operation, this is kind of a mathematical operation, dot and matmul. When we do a dot, right, A dot B,
So how are we calculating -1 and 11?
it is the operation is similar to A dot B, and when we do B dot A, let me just put it also in code over here then. Matrix multiply.
Scroll up, no? One second, just scroll up.
Yeah. Matmul. Okay, so B dot not a line dimension. So basically, matrix multiplication, when you will do a dot product, right? It is giving a same result, but yes. So when you want to do a dot product, right? You essentially do matrix multiplication. It is, you can say, think of it like but would it?
How are we calculating A dot B as -1 and 11?
Okay, I'll show 1 second. I'll just, if we have this array.
One second, let's calculate now. It is same. We already have a screenshot.
Okay, you have, okay, 1 second.
Yeah, in the not here. Just go up, no? Yeah. See, we have A's array like 1, -1, 1, 2, B is 3 and 4. So we have to get this one -1 and 11, no? Okay.
So dot product is in matrices also, right? Matrices also have dot product, cross product, if you are aware. They have inner product, scalar product, and matrices. So when we say matrices, we can have three-dimensional.
No, I'm just simply asking. So like, see, we have A dot B. Okay.
Yeah.
Can you see this A dot B?
No, A dot B won't work because it will think that this is
dot B, not this one. The first one, A dot dot B.
Okay, yeah. A dot B. Yeah, -1. So you were asking how did this come?
Yeah.
Okay. So A is 1 - 1. Dot is, we multiply all of the instances of this number. It is same operation. It is same operation as matrix multiplication. But if you are asking, your doubt is how is a two-dimensional array multiplied with one-dimensional array and we're calling it a dot product. Well, basically, I need
so
to
you
think.
were saying no, matmul and dot
product. Are shall we try it in this console?
No, answer I got it. It is simply same as the matrix multiplication, -1 and 11. Yeah. Okay. Result is same, matmul and dot. Okay.
Okay.
But you mentioned in very first, like these two are different.
So matrix multiplication, there is something. So in a linear, in algebra, right? In algebra, matrix multiplication and vector calculus are different.
The alignment.
Not because of alignment. Think of this. These can be related. Okay? So let me. No, it's not. In matrix multiplication, we are dealing with matrices. In vector calculus, in vector algebra, we are dealing with vectors, but they both are analogous. Dot product for vectors is analogous to matrix multiplication of matrices. If you have matrices and you are doing a matrix multiplication on them, that is analogous to dot product in vectors. So you would get same answers. If you treat numbers like matrices, you do matrix multiplication. Just for clarity, right? If you're writing code and you are writing matmul, it will be more clear that you're dealing with matrix, and if you do np.dot, then it would come out clear that you are probably dealing with vectors. But if we see over here, they are both the same. And dot product the definition of dot product, we can see matrix multiplication we already know, and dot product, if we see over here, A dot B equals to A B transpose. So you see over here, right? When we see A dot B, it's basically multiplication of matrices A multiplied by B transpose. And matrix multiplication is done this way only.
Yeah, to match the
To match
dimensions.
yes, to match the dimensions, you're right. Number of rows in the first, number of columns. So I just explain over here.
Yeah, I know. You can skip
You know,
this part.
okay. And geometric definition, you're aware. If we say A dot B, then this is A modulus of B cos theta. This is also dot product in vectors. It is saying vector over here, and probably it should be saying matrices. Okay, vectors are identified with row matrices. These are interrelated concepts basically. So we should not try to separate them or confuse it. But this is algebraic definition. This is taken from Wikipedia. Algebraic definition says A dot B equals to A multiplied by B transpose. And geometric definition says A dot B equals to modulus of A modulus of B cos theta. Got it? In Python
And the
code,
results will be the same?
and they will result in the same thing.
Okay.
You might think that they would not write. I would need to check it as well, but these would result in the same thing.
Okay.
So modulus of A. So this, you were right that when we are discussing with the one-dimensional vectors, these two look easy to understand. But what happens when the number of dimensions increase, such as 2 by 2 matrix also, even for that simple case, it looks confusing. But base should never be forgotten. I would still suggest that you keep this to your heart, that algebraic definition is this.
The dot product is for vectors.
Yes, the dot product of two
And factor
vectors.
is for
And yes, matrix multiplication is for it's a matrix operation, and dot product
and then
is for
multiply. We have multiply is for simple multiplication.
multiply is like
Simple
point to point,
right?
point to point multiplication, that you minus one is added, minus one is multiplied by
Element per
element
single
by
element
element.
to every.
Yes,
Yeah.
yes,
Okay.
yes.
Okay.
So this we have shown. This is what I was trying. We have A, B, and C. So with one-dimensional vectors, it's relatively very simple. If we have A, point A is over here, 3, 0, X is 3, 3, 0, 3, 3, and 0, 0. 3, 0, 3, 3. Now, if we do A dot B, 3, 0 dot 3, 3, 0 times 3 would return 0, and addition of 3 times 3. So dot product, if we say, I did this is one of the ways to do that, to understand how dot works in one dimensional. This is for 1D vectors. This is pretty straightforward, that we can with lists we cannot do this, but with NumPy arrays we can do multiplication, and it would essentially do a multiplication of element by element, and then it would sum it. And we also see that this is the over here linear algebra and norm, this operation you were seeing, right? Geometric definition. This we would get through linear algebra package of NumPy that has got norm, and if we have a vector, and norm is basically um, modulus. This is the norm, under root of a times a dot a, under root of a dot a, Euclidean length of the vector. This is this. Okay.
Yeah.
So this was about, so NumPy has got a lot of constants. I would show there is a constant called pi, right? We can get that constant by np.pi. Np is NumPy package, and if we want to get the uh, we were seeing right over here that a modulus of a, modulus of b, and then cos theta. Then what is theta? Theta should be in radians. Np dot pi dot 4. Pi by 4 is, your pi is 180, and 180 by 4 is 45. 45 radians. So you get 45 degrees. I think it's degrees. So 45 degrees, its cos theta is cos 45 degrees is, but it's not 45 because this is over here radians. If we do this, it won't give you 45. It will give you this, and this is radians. And we can also check over here. Np dot cos 785.777. So this is clear, right? This is radians. When you
So I
do
was just, you mentioned np dot pi divided by 4. So pi is 22 by 7, right?
pi is 22 by, okay,
Which is
yep,
3.14. 3.14.
yes, 3.14. Yes, you are right. Yes, as you were saying, this is radians basically.
3.14
Yes,
divided by 4.
np by 4.785. Now you were asking how is this giving us,
Yes,
this
it's
is 45.
0.7.
This
Okay,
is 40.
0.78. Okay.
Got it?
So both are giving us the same results, correct?
Both are giving what?
Same result.
Both would give same, no, both would not give same result. If we would do, like you were saying, if we do this,
No, not this.
okay, yeah, np dot pi, right? Np dot pi by 4.
No, I'm not asking about formula. Just go back to the block.
Okay,
What we are doing, we are using two methods. So this,
yes, both are giving same results. Np dot 9 you are seeing, right? Mod of a mod of b times cos theta equals to 9, as we are seeing over here. Okay,
go up, no? Scroll up. 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 Where's the formula?
this,
Yes, this is geometry. Okay. Yeah. Okay. Yeah, you can move on to next.
now with this we covered dot
This
product.
is your blog,
What?
survival 8 dot blogspot.
So this
This
is
is
my
your,
blog. Yeah, I write over here. But
yeah, I can see 9th September 2021. So, yes.
okay, so you can, so this is just This is about shall we, okay, you want to random package? Shall we talk about random package?
Continue tomorrow, or we shall continue tomorrow?
Yeah, we can continue tomorrow. So same time?
I'm okay with today also, but I think the recording. Uh,
No, record. Yeah, well,
if you
however,
I can continue with random and shuffle.
it's basically just a few lines.
Yeah, we can cover this also. Yeah, let's
So this, but this is just very pretty intuitive that we
random numbers it will generate.
random int it will generate. This will shuffle the array,
Hmm.
np dot random dot shuffle, and well, basically with random you can not only get random integer or shuffle, you can also get distributions. I would show over here that binomial normal distributions, for this is a special case of normal distribution and this is binomial distribution. I just show binomial over here. This is mathematics and statistics, part of mathematics and statistics. I have a blog for also for this. If you have a binomial distribution of this kind, right, random package, just an example, you have a flip of a coin, right, trial, you understand, like small experiment. uh, so this is binomial probability distribution. Experiment consists of a sequence of n smaller experiments called trials. So you have an experiment, in that each experiment you have n trials. Now each trial can result in two possible outcomes, success or failure, and each trial is independent and probability in each trial has a probability p. So this is binomial experiment. This is just basically how four conditions, if your experiment meets this condition, the distribution that it will generate would be of binomial probability. You might, it happens that when you would keep learning about it, it might slip through your mind. So just keep use this link as a reference, or write it down somewhere in the meantime, that whenever an experiment meets these four conditions, you have two outcomes, each trial is independent, and there is a probability of success in each trial, then the experiment would be a binomial experiment, and it would generate a binomial distribution as we plot the outcome of the experiment. Like we are overseeing over here, flip of a coin. Let us so what is going on? So the way to get it right, this is showing over here, random. One second.
So is it related to random and shuffle?
This is related to random and shuffle in just in this sense that you can get random packages, not just about getting random integer or shuffling. It has got some other use cases such as getting the distribution. Over here we are seeing binomial, and over here we are seeing that this orange is normal and this blue is binomial. So basically random package is also used to get the distributions. We talk about it later, but for now keep it in mind that random package has got basic three uses to get a distribution. So a use case, right, you might be thinking like, what is the use? But let's say you want, shall I talk about the use case that I have in mind? Just one line.
Yeah.
Flip of a coin. If you want, if I ask you, you are asked to give me the plot the outcome of flip of a coin in zeros and ones for 10 times. Now, how would you give that? Now, flip of a coin has got two outcomes, heads and tails. The probability of success is 0.5 for heads and 0.5 for tails. Well, basically probability of success is 0.5. Each each trial has got only two outcomes, heads and tails, and each time we flip the coin, the trial is independent. The flip of a coin is independent. So this experiment would be binomial, and you can use random package, random.binomial package to simulate this kind of experiment. Got it? Random dot binomial, like over here you're seeing random dot binomial. N is number of trials, P is probability of success, and size is, what is size? I would have to check. Shape. Okay, number of trials is 10. Okay, size is number of times you do the experiment. Number of times you do the experiment. Okay. Each experiment has got what?
Number of trials is different from number of time we do the experiment.
Number of trials is different from number of trials is in. So if you say binomial, right? How do we generate a binomial point? Let's say this line over here. I just copy it in Paint and expand it. Now, if we see shape is 1000 and counter B1. Now, if we count B1, number of times we saw 5. 5 means if we are flipping a coin 10 times, so each of these numbers, you see, what is this number? 5, right? 6, 4. These are the outcomes of the experiment. Getting it? 7, 2. None of these would be greater than 10. Why? Because we have only 10 trials. Each time we would do a heads or tails, we would get either 5 or 6 or 4 times, or see on the more the extreme, how many times did we get all zeros? Only 4 times. And how many times did we get 10? Only 2 times. But the thing is, number of trials determines the size, the range of this outcome, this output. 5, 6, this is the output.
So we are flipping a coin. You mentioned flipping a coin.
You are flipping 10 coins. Number of trials is 10, right?
Okay, flipping 10 coins. Okay.
And number of trials is 10. 10 coins, or you flip one by one, each is same. You flip a coin 10 times.
So we are flipping 10 coins at once, okay? Correct?
Okay. Yeah. So you are rephrasing the same thing. You flip a coin 10 times, or you flip 10 coins, you would get some kind of output. Got it? If you flip a coin 10 times, or you flip 10 coins, you would get heads or tails, heads, tails, heads, tails, this, right?
Mm-hmm.
So if you have flipped 10 coins, and you would get some heads, but number of heads would never be more than 10 and would never be less than 0.
Mm.
So when we initialize a binomial, the experiment I gave to you to plot them, this is how you can do it, except that this is a fair. Probability of success is 0.5. That means coin toss is fair. Number of coins that you are flipping is 10. And how many times you are flipping? 1000. Now, number of experiments, 290 plus, 1 second. I show here. These numbers, 290 plus 200 plus
These are
1.
equals to 100,000.
Yes, it will be equal to 1000. So size tells how many elements you want. B shape of b1 is 1000, and this determines kind of output you would get, how many successes is the right term. Number of successes in the first experiment is 5, number of successes in the second experiment is 6, number of successes in the next experiment is 4, and so on. Getting?
So why it is shuffled 5, 6 number of first
Yeah,
time you are saying?
because this is a random experiment. This is coin toss. Agree? So when you toss 10 coins, highly likely.
I think what I can understand from this one, we have 10 coins. The first time we are getting the result, like suppose
Five heads, five successes, 5 heads.
5 times. No, wait. 5 times heads we got in 290 times we got 5 heads. 200 times we get 6 heads.
Yes.
186 we got 4 heads. Like that we are getting the answer.
No. Okay, no. Not one. No. This is 5 heads. In you do an experiment.
Anything heads or tails. Like 10 is only 2 times we got all the 10 heads or all the
Yes.
10 tails.
Now you are right, because the more you
The similar. 290 times we got
5
half and half tails.
half. Yes. 290 times. Yes, you got. Yes, right.
Yeah.
Yes. So this
I
is
said the same thing previously also. Yeah.
okay. So
Okay,
this
so
is
counter even is just shuffle.
counter. Okay, counter I did not explain.
It is coming like no. It is giving in the descending order. It is giving the answer 290, then 200, then 186, 116. Okay, count. It is counting in descending order.
Yes. It's
Okay.
counting in descending order. Yes, you are right. So this was all for today. Shall we connect again tomorrow?
Yeah, okay, sure. We can connect tomorrow.
So I'll prepare something and we discuss. Do you have any specific request or?
No request. I just want to work on this NumPy and Pandas. 4 Python actually I want to work on. So yeah, let's see. We'll work together.
Yeah.
Okay. You
So
can explain me.
yeah. We'd continue with this thing. Well, basically one thing is left. If you want, I can show it to you. Maybe tomorrow, or if you want.
Yeah, you can. Yeah, we can continue tomorrow.
Okay, one second. Okay, then continue. Then we'll continue. Okay, no, I think I'd explained this. Doc test, did I explain?
No, not this one.
Okay, maybe we'll discuss it tomorrow then.
Okay, yeah, sure.
Okay, bye. I'll call you.
Yeah, okay. Bye-bye. Thank you.
You too. Thank you. Bye.